Okay, in this video we're going to use curve sketching guidelines to sketch the function f of x equals 1/2 x to the power 4 minus x. And you're probably wondering what I mean by curve sketching guidelines. Well, in most calculus courses you're expected to have certain features included in your graph, and we refer to those generally as curve sketching guidelines. Now, there's not one completely consistent set of guidelines, but I'm going to just go over probably some of the most common guidelines and features that you would be commonly expected to include in a graph of any function. Okay, the first guideline, or I guess characteristic you should consider when sketching a function is the domain of the function. If your function has a very limited domain, then of course that should be obvious in your sketch as well. The second thing you should consider is to include your intercepts. Your y-intercepts should probably always be included, and if your x-intercepts aren't too much trouble, they should be included as well. And of course, that's a little bit of a judgment call, that part, but some x-intercepts are impossible to find analytically via pencil and paper, and some are maybe not even worth the hassle, like some polynomial functions. But it's something you should at least consider, and if it's not too difficult, include in your sketch as well. The third item, which is kind of related to part A, but if there are actual asymptotes in your function, well, those should be present as well, and typically in dashed or dotted lines as well. So horizontal asymptotes, vertical asymptotes, and even slant asymptotes. And then the next pair, which is probably we're expecting, they're both in the same color because, of course, both of these items are related to your first derivative. So you differentiate your function, and you obviously want to use some calculus in a calculus curve sketching question. So make sure you consider that the intervals of increase, what they are, and make sure your sketch is consistent with the correct intervals of increase or decrease. And related to that, of course, make sure if you have any local max or mins that those are included as well, and the exact coordinates, or I guess even decimal approximations. If it's too much trouble, decimal approximations would be more than reasonable as well. And that brings us to the letter F now, which I guess predictably as we move on to our second derivative, and make sure that we include concavity and inflection points if there are any as well. And then once you get all that done, try to, make sure all those pieces of the puzzle fit together to give you a coherent sketch, including all of those items, A to F. Okay, so here we are, back to our quartic, or degree 4 polynomial function, and see if we can use those curve sketching guidelines to sketch the graph of this function. And keep in mind, the curve sketching guidelines are not completely consistent, from course to course or text to text, but again, those are the most common guidelines that I think you will find in most courses. And also the order doesn't have to be completely consistent either. There's no prescribed order for these guidelines as long as everything is considered. So I'm going to keep the same order that I just presented moments ago. I also like this order because it gets the non-calculus stuff done as much as possible up front, so you don't have to worry about it later. So first things first, the domain of this function. There's nothing to worry about with the domain of a polynomial function, any polynomial function, and definitely not a degree 4. So we just have to make note that our domain is the set of real numbers. Letter B. Intercepts. So first things first, we'll get our y-intercept, because that's never too much of a problem. So the y-intercept is going to be evaluating our function at 0, and we're going to get a whole lot of 0. So this function goes through the origin. So that means we actually found one of our x-intercepts as well. Now the x-intercept, set y equal to 0, and ask yourself how much trouble this would be to solve. And hopefully you wouldn't be too concerned by that equation. You can see a common factor. So of course it's a degree 4 polynomial, which is a little harder than a quadratic, but it's still relatively the same kind of an approach. And I think I'm also going to take a common factor of a half out as well. That's kind of optional. So if we take an x out, that's coming down to x cubed. And I also took the coefficient out with that as well, of course, the half, which means I won't just have a 1 left here anymore. That'll actually be a 2, because 2 times a half, of course, is 1. So you can double check your common factor by expanding that out to make sure everything looks good. And then you realize, yeah, that wasn't too bad. We can find all of our intercepts now. So whatever makes our first common factor equal to 0, which is a half x. We already know that because that happens to be our y-intercept as well. And I guess the other information to consider is how to make x cubed minus 2 equals 0. So we would get the x cubed by itself, and then of course get rid of the x cubed, so that would require a cube root. And remember, anytime you take an odd root, you must not include pluses or minuses. That's only when it's an even power, or that you're getting rid of with an even root. So that means we found our second x-intercept. Okay, and the next guideline to very briefly consider would be, are there any asymptotes for this function? And since this is a polynomial function, of course there are no asymptotes of any sort, which means we can move right on to letter D and finally start some calculus. Because D is intervals of increase or decrease, and once we have that set up, then we can roll right into letter E and classify any turning points that we find as local mins and maxes. So the next two steps pretty much go together. So we need our derivative first and foremost. So f prime of x is going to be a half times 4x cubed, or we will say 2x cubed minus 1. And since that's a cubic polynomial function, our first derivative, of course, it can't be undefined. So our only critical values are going to be whatever makes this equal to 0. So what makes 2x cubed minus 1 equal to 0? Well, we'll add 1 to both sides and divide by 2. And then we'll take cube roots. And remember, with a cube root, you do not add a plus or minus. That only happens when you have even powers and you're using an even root with an even index. So this is going to be the cube root of a half, which I think we'll just say cube root of 1, which is still 1 over the cube root of 2. And there's our, I guess, sole critical value for this function as well. Okay, so now time for a sine diagram so we can determine our intervals of increase or decrease. And I'll put it right here beside our derivative. So f prime of x. And our only critical value is 1 over the cube root of 2. Now, incidentally, if you want to check that on your calc, if you'd rather work with the decimal, that might be wise. This is roughly 0.79. I guess I'll go 4 decimal places, 7937, which means we can test 1, of course. The other way to figure that out without a calc is cube root of 2 is bigger than 1. So, of course, this 1 over cube root of 2 has to be smaller than 1, which, of course, we can see maybe better in decimal form there. So let's plug in 1 into our first derivative, and we'll get 2 minus 1, which is positive. And that tells us our function is increasing because, of course, these are all positive tangent slopes. And to the left of 1 over the cube root of 2, 0 can go into our function. That's a convenient x value, and that's all gone. We'll be left with negative 1. So our function is decreasing, which is evidenced by the negative tangent slopes as well. And now we can say our critical value, which incidentally I never did label, that's our sole critical value. I think that's obvious from the sine diagram here. Now we can determine that there's a change in function is changing from decrease to increase. So of course this has to be a turning point. So we have a turning point. So let's classify that turning point as we now, I guess, move on to letter E. So since this critical value made our derivative equal to 0, right now it was a stationary point until we saw the change in the tangent slopes. And that one's a bit wonky. Change in the tangent slopes from negative to positive. So of course we can now move on to letter E and call this thing a local minimum. So why don't we just say that right here. Local minimum, and of course that occurs at, I think we'll just use decimals. Of course you can feel free. Actually, I think I'm going to double back. We'll get the exact value. And if you want to just bypass this and just use decimals, that's fine as well. So let's say 1 over the cube root of 2, because that means we'll have to do a little bit of busy work to get the exact y value, which I will do because I think it's important to have some radical chops when you're working with derivatives and working with calculus. So very quickly here, if I evaluate f of x at 1 over the cube root of 2, foolishly without a calculator, to get this y value, of course, this is going to be 1/2 of that x value to the power 4 minus that x value. 1 over cube root of 2. Okay, so we're going to have 1/2 multiplied by 1 to the power 4 over the cube root of 2 to the power 4, which is the cube root of 2 to the power 4, which is 16. And we can simplify that in another second. And I think we can get common denominators here pretty easily by the looks of things, because we got a cube root 2 on both sides, so this isn't too bad. If for some reason somebody insisted that you got the exact coordinates of your local minimum here. So that can simplify. That's 8 times 2. So on the bottom there, if we simplify that radical, this is going to be 1 over 2 times the cube root of 2, because of course the cube root of 8 is 2. And that's going to be, and let's just maybe slow it down. We'll do 2 more steps here. So this is going to be 1 over 4. I guess it's really one more step. Multiply the 2's on the bottom. So it's 1 over 4 cube root 2 minus a lonely cube root 2. So of course we're going to multiply top and bottom of that second fraction by 4 to get a common denominator. And there we have our exact y value is going to be 1 minus 4, or negative 3 all over 4 cube root of 2. So that didn't take too long, and that's probably a good, I guess, review of radicals that you may or may not have needed. So we'll put in a negative 3 divided by 4 multiplied by the cube root of 2. So again, that's a local minimum value, and those are the exact coordinates. And when we go ahead and try to sketch that in a few more minutes, I think we'd probably switch this to decimals. So the decimal representation, I already wrote down the x value, but that's 0.7937, and that y decimal approximation is negative 0.5953. And I think the decimal approximation is probably far more useful, of course, when we go ahead to sketch this. But we still got one more section to get through before we sketch. Of course, we're going to move on now to letter F. Okay, so determine the concavity of this function to see if there are actually inflection points. Of course, we need our second derivative. So f double prime of x is going to be the derivative of 2x cubed, which is going to be 2 times 3x squared. And then the derivative of negative 1, of course, is 0. So there's no way we can make our second derivative undefined, but you can probably just look at that and say, well, how do we make it equal to 0? Well, how do you make 6x squared equal to 0? And there's only one way, of course, and that is x equal 0. So there's only one possible inflection point. Now, I'll be honest, with a cubic polynomial, when I see that that I have a value that makes the second derivative 0, I could probably expect that I have an inflection point and assume that I have an inflection point. But the reason we have this example here in our curve sketching exercises and our curve sketching examples is to make sure you don't jump to conclusions. Make sure you still do your Sine diagram. Because if we think about 6x squared, if I put negative 1 or positive 1 into this Sine diagram here, it's going to be positive everywhere. And if you want to visualize the function 6x squared as a quadratic opening up with a vertex at the 0, this will also make sense that it's positive everywhere, which means this is not an inflection point because our concavity doesn't change. It's going to be concave up to the left of 0 and also concave up. So I guess don't jump to conclusions with your first or your second derivative Sine diagrams. Make sure you take the time to consider the behavior, in this case the concavity of this function, by examining its second derivative. And we can see if the concavity doesn't change, then I can't call this an inflection point. So I guess what do we call this thing? Well, this is actually called a point of undulation, or an undulation point. And that's one of the most common ways of, I guess, common terms for this situation. An undulation point is kind of unusual. but I guess it's not too rare to have when you get into higher degree polynomials. Your second derivative is 0 here, but since the concavity doesn't change, not an inflection point. So what will we see? Well, with an undulation point, you typically see a flattening of the curve in the vicinity of this point of tangency. It becomes very, very flat. And I guess you could say it's at least qualitatively it loses its curvature. You will also see when we look at Desmos here in a few more minutes is that the point of tangency at 0 and 0 does not slice through the curve like it would at an inflection point. It remains tangential to the curve. So to be clear, as we wrap up our concavity, we have our concavity is up everywhere, and we don't have an inflection point due to the fact that concavity doesn't change. And we have, I guess, another new term thrown into your calculus terminology here as an undulation point, where our second derivative is 0. So we would expect to see a flattening of our curve, but definitely not a change in concavity. Okay, so here we are finally at letter G, where we get to assemble the pieces, the puzzle pieces to sketch our curve. And the first thing we found, I guess that we're using here were the x-intercepts, and we have one at the origin and one at cube root of 2, which is roughly 1.26. We have our decreasing and increasing intervals on either side of now what we can call our local minimum value, which is approximately at 0.8 and negative 0.6. And then over here, that undulation point, of course, was one of the strangest features of this function, and probably the reason I included it as an example here is that the undulation point is at 0 and 0. The concavity doesn't change on either side of that undulation point. It's concave up on both sides, and I also put a straight line kind of a segment just to show you that at an undulation point your curve tends to get really, really flat and loses its curvature. So without further ado, here is our function, and you can see all of our pieces fit together. And I guess the only thing I didn't bother to consider, which is kind of related to asymptotes. Now, since this function doesn't have asymptotes, you'd be foolish to try to look for asymptotes on the function, but you can also think about your end behavior of this function as well. If you're familiar with the end behavior of a even degree polynomial with a even leading coefficient, probably makes sense that this function is opening up and exiting, I guess, quadrants 2 and 1, as this function is doing. So let's take a quick look at this function in Desmos and explore, I guess, the tangent line behavior around that undulation point as we wrap up. Okay, so here we are in Desmos to take one last look at this quartic polynomial function. And remember, maybe we'll look at the intercepts first. The x and y intercept there are going through the origin, and there's our other x-intercept, which remember was the cube root of 2, which is approximately 1.26. And our local minimum value and the exact coordinates are over here in the input area in Desmos. You've forgotten those, but of course I think we'll just call it approximately 0.8 and negative 0.6. And incidentally, I've been referring to this ordered pair as a local minimum value, but as you can see here, and you probably saw this before, there's no y value smaller than approximately negative 0.6 or negative 3 divided by 4 cube root of 2. So it's not just a local minimum value. We can actually call this an absolute minimum value. So I wouldn't worry too much. When you're working with your first derivative and classifying turning points, go with the local, I guess, terminology. And if you at some point in your sketch realize you have an absolute turning point, in this case a absolute minimum, then you can just use that terminology as well, which is a little more correct. But local is still acceptable as well. So we got an absolute minimum at approximately 0.8 and negative 0.6. And now, of course, let's look at that undulation point in a little more detail with our tangent line. We can zoom in and see that that tangent line definitely does not slice our curve. There is a little bit of daylight between the function and this tangent line. Remember, it looks like they are intersecting at more than one point, but of course they're not. This tangent line is only touching this function at that point of tangency. So if I continue to zoom in and mess around with the window settings, we could still see a separation between the function and the tangent line. But I guess most importantly, we can also see how relatively straight that function is at the undulation point. So one last thing, let's just consider our other tangent line features, I guess. I think you can see that we have negative tangent lines up into that absolute minimum value, so that's why we recognized our function was decreasing because of those negative tangent values. And then after our absolute minimum, we have positive tangent values, which tells us our function was going up again or increasing. And you can also recognize that all these tangent slopes are underneath the curve, or I should say tangent lines are underneath the curve, even at that point of undulation. And that's, again, evidence that we have a concave up function everywhere. Okay, so that's a wrap for this example, and as I'm sure you've noticed, curve sketching is not for the faint of heart. It's a time-consuming process, and in this video at least we looked at some common guidelines that you can use to guide you through this time-consuming process, but it is not much fun, but it's an essential part of calculus, because without being able to sketch and I guess hence understand functions, you're going to have a lot of problems when we look at some other applications of the derivative.